And if you can imagine moldy green cheese as the surface of
Okay.
Mercury.
You're listening to The Cosmic Cast. Hello and welcome to another episode of The Cosmic Cast, brought to you from the Earth and Solar System team at the University of Manchester. I'm John Penney-Fisher and I'm joined with my regular co-host Marissa Lowe.
Hello.
And this week down in Milton Keynes for the Open University, joining us is David Pegg.
Hello.
How's it going?
Yeah, good, thanks. Good, thanks.
Well, first, congratulations on submitting your thesis very recently. That's excellent news. And
Thank you.
so, really, I guess one thing that's occurred to us is that we've not really touched on Mercury at all on this podcast. And you, David, I believe, are the man to talk to about all things Mercurian.
I have spent the past 3 and a bit years looking at the planet, so I hope I know a thing or two about it by now.
Yeah, I'm sure you do, absolutely. So you've been doing a lot of mapping, is that right?
Yes, so the planet is divided into 15 different areas, and NASA went there in 2008 and took images of the whole planet. So the first time we had global coverage of the whole planet with images, and my job is basically to map 1/15 of the planet in preparation for future missions. So the European Space Agency and Japanese Space Agency is on way at the moment, and really these maps will help us understand the geology of the surface of the planet and plan for future imaging campaigns.
Yeah, so I guess that's the messenger mission that most of your data comes from, isn't it? I didn't really realize until fairly recently, just quite how little we knew about Mercury really prior to the messenger mission, I suppose.
Yep. So the first mission went there was in the 70s. That was called Mariner 10, and it was actually the first mission to use flybys. So it flew by Venus to help it slow down and get close to Mercury, but it didn't actually orbit the planet. It flew past 3 times, but due to coincidences of the timing, it flew past the same side 3 times. So we had no images of half the planet until 2008.
Yeah, that's incredible. And so, you have all these pictures and stuff. How, I guess, what's the process then of going from these? I guess they're equivalent, I suppose, of like satellite photos in a way, aren't they? Would that be a fair analogy? And then
that's exactly what they are. So initially they are put together, but a team from Messenger actually produced a global mosaic. So they stitched all the images next to each other that were taken roughly the same time of day to try and then build up a whole mosaic of the whole planet, so that there is a continuous map of the surface now made out of these separate images. And then it's this that I've cut out my individual part of the planet, the Debussy quadrangle, and that's what I use to map. I also have used some individual photos, some individual satellite images, and we know where the satellite was when it took the image, and so you can then locate where it should be on the surface of the planet from the data inside it. And that's used to look at the surface, and that's part of my mapping process, is to look at the surface and look at the different textures, the different features, the geological features, and try and build a picture of what it looks like now, and that builds an understanding of eventually how the surface came to be as it is now.
Yeah. You must really have to get your eye in then to look at all the subtle differences in, because presumably it's all mostly quite grey, these images.
Yes, it's very grey. In fact, if you look at the moon, you've got the sea at night sky, you've got the Maria, which are the seas, they're the dark basalts, and then you've got the lunar highlands. Mercury doesn't even have that much contrast, so it's all quite a low contrast planet. But luckily, you can use image processing to enhance that a little bit, and also you need shadows. So depending on the time of day, you get a different amount of shadows. So there's no atmosphere around Mercury, so the light is directly hit. So any part that's completely in shadow, there's no diffuse light there, really, and so you can't see anything where that shadow falls. But if you have a mountain or a cliff, that cliff will produce a shadow if it's kind of in either mid-morning or mid-afternoon. But midday, when the sun's overhead, the shadows completely disappear and you can't pick out any textures. So you can use different times of day to work out and study different features and different textures of the surface.
So, being another rocky body in the inner solar system, I imagine that Mercury would be quite similar to, say, the Earth and Moon. Do we see a lot of similar features between these different bodies?
Um, there are some similarities. You've got similar processes that go on, but they might be present in different ways. So one feature are rupees, which are large cliffs on Mercury, and these are formed by tectonic faults. Now we have tectonic faults on Earth forming things like the Himalayas, and between all the different continents that move apart. Mercury doesn't have continents in the same way. It doesn't have plate tectonics. It's just a single thick crust, but that crust has still got these faults that happen at moving them, and they cause these large cliffs that can be thousands of kilometers long and to 2 kilometers high on the surface.
So, do we think that Mercury has been very tectonically or volcanically active during its history?
The short answer is yes to both. It's still, in fact, we think tectonically active. Some of the higher resolution images from Messenger showed some very faint cracks near to some faults, which suggest that they'd moved very, very recently. And they also have covered over some small impact craters. And the smaller the impact crater, the more recent we think they're likely to be. So some of them have been covered over. So they're still very much active. And then there's definitely volcanism in the past. The whole surface of the planet is in fact probably volcanic. On the moon, that brighter area, the lunar highlands that you see, that is thought to be a kind of like a primary flotation crust from when the moon's surface was cooling from the magma ocean. Mercury, we don't have that original proto crust exposed as rock on the surface. Instead, it's just layers upon layers of different generations of lava flows. And on the moon, in fact, I think that picture behind you is a lovely sinuous rill. We don't have any of those on Mercury. It's quite odd. There's lots of flooded basins and things like that, but there are no signs of any features like sinuous rills. We think that's probably due to the fact that the lavas are very much a lower viscosity, but it's still a bit of an outstanding question for Mercury, why we don't have those sinuous rills.
I guess, I mean, is there good sort of chemical data for Mercury in the same way that we have for the global maps of the moon and stuff?
Well, the moon we're lucky in that we've got samples from the moon. Unfortunately, there are no known samples of Mercury. There might be 1 or 2 meteorites in a collection that could be from Mercury, but they've not been classed as such. So we have to rely on the remote sensing data. And they give us some broad ideas of some of the compositions, and they do actually show that Mercury is a bit weirder than, say, you'd expect compared to the moon, or even compared to Earth. It's the basalts, the lava on the top of the surface. They're very low in iron. So I think the moon is at something about 15-16% by weight iron.
Iron rich, yeah.
Iron rich on the surface, whereas Mercury's lavas on the surface are very much iron poor. They've got less than 2% iron in them, so it's very low. At the same time, Mercury's crust is incredibly carbon and sulfur rich. It's got like 4% sulfur in it and 1 or 2% carbon, which compared to the moon, where it's a fraction of a percent, it's really quite rich and volatile. So it's these volatile lighter elements, which is quite surprising, really.
So I guess do you sort of use these kind of chemical maps that people have made to sort of help decide what kind of lithologies you're looking at when you do your mapping then?
So not with the work that I'm doing. Mine is really a morphology map. So by that, we mean that we're looking at the different textures of the surface, and we use that to work out the history and the story that goes on there.
So it's more of a sort of a tectonic map rather than a sort of a lithological map then?
Yes. I mean, there's also other features in it as well. We look at the volcanism, and also I look at impact craters and the different the amounts that they've been kind of degraded by space weathering and later impacts to work out the age. So it builds up a texture of the surface, because older lava flows will have more impact craters on than younger lava flows. So I can say that they are older areas on the planet.
So I suppose for a lot of geologists listening to this, they probably picture mapping as, you're in Scotland, you have a clipboard, you're covered in waterproofs, you've got really expensive mapping pens with you. What's the process of mapping Mercury like then? What are your tools? What's your software and so on?
So I use a geographical information system. I use ArcGIS, but it's basically the same as QGIS. They're the two main ones that are used. And I have multiple different images loaded up from different illumination angles, whether it's like in close to the morning or close to the evening or midday. And then I start to draw out the first features I look for are large impact craters, and then these cliffs, to try and draw out the lines to work out where the geological structures are, and where the impacts have occurred, and then start to then break those down, map out where the ejecta for these craters are, and then I'm left with all the areas in between the crater and the tectonic features to then work out what's gone on in those regions. And that's then looking at those surface textures. Are they quite hummocky and deformed, or are they very smooth and flat? Are there very fine little cliffs in them? We call them wrinkle ridges, and that's a sign of I'm going to say recent lava flow, but in Mercury terms, a recent lava flow is about 3.5 billion years old. So things like that. And then also start to look if there's any extensional features. So in some of the lava filled basins, impact basins, as they cool, the lava shrink and they crack and you get grabens forming. And you also have isostatic effects where if you've moved a large amount of crust off the surface by an impact event digging out a basin, the underneath is going to want to then react and lift up because it's no longer got the weight of the crust on it in the same way. So you get these extensional cracks also forming inside these basins. And then finally, I start to look at things like we have these explosive vents, which create pits in the surface, which have bright halos around them, and start mapping those out.
It's an amazing amount of detail you can tease out from all these images then, really. So do you have to coordinate with the people who are mapping other quadrants to sort of get sort of consistent sort of nomenclatures and units and all that kind of stuff then? Is that process quite challenging, or?
It's definitely something we've had to bear in mind from the very beginning. So mine's not the first map to be done. Valentina Galuzzi created one for Victoria quadrangle from the from the messenger data. But even that, she then looked after Mariner 10, they did do maps at a larger scale. So they did it at 1 to 5 million, which means that every millimeter is 5 kilometers. So you could easily hide a village inside that. But they completed maps and they looked at things like the crater degradation, the age of the craters, and the different dividing up the plains, those lava plains, into different approximate morphologies and ages. And so she then went and said, is this the mapping that we can do now with the messenger data, which was at a scale of 1 to 3 million. So 1 millimeter on my map equals 3 kilometers. And then from that created a mapping standard, and then that's applied to the other maps, and we're talking with each other. And just the last couple of weeks I've been working with Chris Malaband, who has been mapping the quadrangle above me to the north, the Terrain quadrangle, and making sure that our lines finally meet up. We've always had discussions in between because we've got a 5-degree overlap each side so that we can check that they match up, but we've been doing the final little reconciliation on those.
That's cool. So in principle, when you put them all together, you've got something that's fairly seamless, I guess.
Yes, yeah, exactly. So it should all produce one large global map as well at the end of it.
What resolution are these images that you're working at?
So most of the images are at 166 meters per pixel. So if compared to pretty much every planet and any other rocky body in the solar system, apart from Venus, they're pretty low resolution, but they're better than nothing. So yeah. And there's still an awful lot you can pick out with them. You can definitely make out the main regional features and work out the histories.
Have you gotten the opportunity to name many things within your mapping area?
Yes. So I've got to name a few of these rupees, these tectonic fault cliffs. One was Meteor Rupees, which is named after a German research vessel. All the cliffs are named after various different expeditions and research trips. And then I've also named a couple of craters, one of which I named Travers, which is named after the author of Mary Poppins, because the theme for craters on Mercury is kind of artistic people or creative people. So yeah,
That's really cool. That's amazing. So, yeah, so I guess so yeah, I guess there were the guidelines you had to follow. Then you couldn't just name it after friends and family.
no, not at all. There are definite rules for all the different types of features on Mercury.
Yeah.
And so you've got to kind of suggest something. Some of them might be taken, some of them might not be, depending of if there's a similar name on another planetary body, they try and reduce that, or maybe there's a whole range of criteria that you have to jump through.
That's amazing, though. So presumably a panel sits down and then decides whether to accept your name or not.
Yes, part of the International Astronomical Union, they have a subdivision that looks after this, working with the USGS to maintain standards.
That's
cool. I mean, it beats having to pay to get a star named after you or something like that.
Yeah,
exactly.
Not take the mick out of that too much, but that's quite cool.
Yeah, I mean, that's the name that's going to be there permanently, isn't it? That's brilliant. Yeah, I'm quite jealous of that.
So you said that Mercury's been split into these 15 quadrangles then, and you said that, different scientists and PhD students have been working on mapping these. How far through all of that are you?
Four are peer-reviewed published, and I think they've been stitched together now, so there's actually a complete band. And then another two are in process, I think, of being submitted very shortly. That's my... And then the various stages of being mapped, or it will be started to be mapped very shortly. So they've all been assigned and people are working on them, but it's an ongoing at this stage.
Yeah.
Do you know how were they assigned in the first place then? Did people have to sort of, because presumably it was NASA that sort of divided all these things up then? Did you have to sort of write a proposal or a case to sort of take a particular quadrant? Or
so NASA are dividing it up. Basically, they're mapping the whole planet as one lower resolution, so larger scale map. And we're now doing these finer individual quadrangles because they're a bigger task, but it's being divided by more people. And that's being done by a group of people across Europe, kind of linked to Bepi Colombo, and thinking about assigning targets for the cameras, what they're going to image when they get there, and looking for interesting features.
Cool. Yeah, I was going to ask about Bepi Colombo actually. So I guess that's the European mission then for people in the audience who are not too familiar. So I guess does your team in the Open University have much involvement with Bepi Colombo?
So my supervisor is also working on with the size team, and he's looking after the surface and composition working group. Sorry, not size. He's looking with an instrument called MIX, which is made and built by Leicester University, and that's an X-ray spectrometer. And there's also he's got links to Symbiosis, which is a imaging camera, and that's going to take the high resolution images. But most of the OU's link is through a working group for Bepi Colombo, the Surface and Composition Working Group, which is looking at these different features on the surface and working out what's best to study.
So synergistically, that's great then, isn't it? You can tie in directly what you guys are doing with the mapping to what this future mission is doing.
Exactly.
Yeah.
So as someone who does lunar volcanic features and things like that, I'd love to find out more about any volcanic features that you saw in your mapping area. So you mentioned, is it faculae before? Sort of these vents where it's evidence of sort of explosive volcanic eruptions. I suppose for Earth, we know that we have the effusive eruptions and explosive things as well for the moon. What do we think volcanism was like on Mercury? Do we see a range of different features representing that volcanism?
Yes. So, and in fact, one of my extra bits of research I've done during my mapping was then to do a global study of some of these explosive vents. So we have these effusive lavas that we don't really know where their vents come from. They're so flowy, they're so low viscous, flow so much that they've probably covered over many of the parts of their vents that source them.
Mhm.
And then we have these explosive vents which excavate out holes in the surface of the planet that's, they can be tens to hundreds of kilometers across, and then they have these hundreds of kilometers. We call them, as you say, faculae, the high red albedo features, so they're very bright. um, uh, that feature is thought to be the kind of the volcanic deposits around it that have been thrown out by the explosive eruption. And then you with this central pit that's been excavated or collapsed down the middle of them. Interestingly, they don't seem to have much of a constructive edifice around them, so we don't have any. It doesn't build up. The surface gravity of Mercury is so low, and because there's no atmosphere, it gets quite diffused and spread out so much it doesn't really build up
Mhm.
to any appreciable slope.
Mm.
There are a handful of, I think Jack Wright identified, which look like little cones on the surface of Mercury, and they've got a very coincidental crater on the top, and that
Mm.
coincidental crater also has a slight red albedo. So we're tentatively saying that they are a constructive volcanic feature, like but that's pushing the limit of Messenger's resolution, so we won't be able to confirm whether they are or not until Bepi gets there.
Mm.
Um,
Is there
so-
any sort of pattern to how these features are distributed across the surface?
so they tend to be. There's some areas of very large, smooth plains, we call them. They're the most recent large scale effusive volcanism lavas, which were about 3.5 billion years ago. And those ones have fewer of these pyroclastic features. They don't have any of these faculae with vents, whereas some of the older regions possibly do have more of them. But it's not clear if that's just because the lavas have covered them over, or if it's a difference with internal supply of magmas or volatiles that cause these explosive eruptions, because you need your lavas need to have some form of volatile in them. In the case of Mercury, it's probably carbon monoxide and sulfur dioxide coming out, causing these explosive eruptions. And maybe you don't see that as large as smooth plains towards the north of the planet, but that's not quite clear yet.
Yeah. So will there be data hopefully coming from Bepi Colombo that will help you understand these explosive features more?
Very much so. One of the work I've been doing at the moment is I've been classifying these events as if they are, we call them compound or not compound. But what that basically means is, are there multiple volcanic vents? Are there multiple overlapping craters from where it's exploded out? Or is it just one single vent that's just erupted and possibly once? Obviously, if you have more vent sites, then that suggests that they've been erupted multiple times and there's been more activity at those sites. But what I'd like to see, and we don't quite have the resolution of any of the geochemical data from Messenger is not quite able to see it apart from the biggest facula. What I'd like to see is in those faculae, those deposits around them, do we have multiple geochemical events? So are there signatures of multiple eruptions with different compositions, for example? And that would be really useful. And we'd also get better resolution images, because there's probably at least 10% of them I wasn't able to classify at all, and another 15 or so percent I think just couldn't resolve well enough whether or not they had these categories to see whether they had multiple eruptions, because we don't have the resolution of the data. So both better image data and geochemistry will help us build so much an integrated picture of how these features have evolved over time.
Yeah, I guess it's always the way, isn't it? More data and more information required. So I mean, I hypothetically then, if there were to be some kind of like sample return mission to Mercury, then what sort of areas would you sort of favor going to based on?
Oh, well, earlier on, I said that there's no evidence of rocks that are the original flotation crust, as you see on the moon, that lunar highlands, those white bits, and that's true, quite true, because they have excavated this very much in enhanced spectral images. It looks really dark blue, and this is the stuff that's really enriched in things like carbon and sulfur. And they're some of the features I'd like to get a sample back of, because areas associated with these also have these other features on Mercury, which we've not touched on yet, but I think they're probably the weirdest part of Mercury, and they are hollows. And if you can imagine moldy green cheese as the surface of Mercury, they're kind of depressions that are a kilometer in scale and tens of meters to hundreds of meters of deep, and they have this bluish color, slightly bright around the edge. They're very odd. We think because they have a slight bias towards slopes that are facing the sun, and they're caused by the sun vaporizing rocks that are high in sulfur and potentially carbon, and creating these depressions in the ground from the intense bombardment of radiation on the surface of the planet.
That's really weird. So I guess you're sort of suggesting then that these could be something quite primary in composition. And I've certainly read like some pretty crazy papers that suggested that like maybe the primary Mercurian crust might have been like had some weird like carbon-rich minerals and stuff. Is that still sort of the favored hypothesis?
Yeah, had basically a graphite, the stuff that you get inside pencils, crust very early, and then quite quickly that got covered over by lava flows, and so it's only where big impact events excavate these up and bring them to the surface. But even some of the oldest lava flows would still have been quite rich in some of these materials as well. So
I guess I guess that sort of leads to some quite interesting questions then about sort of what the starting composition of Mercury was and what the sort of parent material that accreted to form. I suppose. I guess are people sort of suggesting that Mercury formed from predominantly more sort of carbon-bearing like Carbonaceouschondrites and things like that then, or?
Yes, yeah, they're looking at those kind of compositions, or Instanticchondrites, things like that. There's no direct analogy because while I've talked about the crust of Mercury being very iron depleted, it's actually the planet as a whole has a huge amount of iron inside it. Its core is more than 50% of its volume-ish, 55% of its volume.
That's big.
Compared to Earth. I think both the Earth and the Moon somewhere around 20%-ish.
Yeah.
So it's really just a large ball of iron with a thin coating on the outside.
Yeah.
But because of the redox reactions, you've got all the iron is partitioned out into the middle of this, and so you've got that interesting and unusual chemistry on the outside. I think it's the most reduced body that we know of, certainly in the inner solar system.
Yeah, I think you're right. And in fact, you just mentioned Instanticchondrites. You reminded me that I think I've read somewhere that there are some people that advocate Instanticchondrites are from Mercury, aren't there?
I think there was one sample of one particular Instanticchondrite that was linked to Mercury, and then there was some other. I think maybe it's thorium and potassium ratios off or something like that. Its signature was similar but not close enough. I think it has been discounted now, but don't quote me on which chemical elements it is, because I am I color in maps. I'm not very good with chemistry.
Yeah, but I guess that's quite tantalizing, isn't it? That you never know when the next meteorite we find might be that missing piece that we're missing from somewhere like Mercury or something. I guess that's
I think I did read somewhere that they've done the statistics and looked at the chances of a meteorite coming from Mercury versus the size of our collection, and they expect N to roughly be equal to 1 at the moment.
Wow.
So there might be one somewhere, or maybe we'll pick it up next week somewhere.
Yeah. Well, that's what I've always said about these people that go off to Antarctica and stuff to collect meteorites. It's just like they're bringing back potential trays full of nature papers, and you never know what's going to be in them, I suppose.
I mean, it sounds like there's so many interesting questions to ask about Mercury that are still unanswered. Why do you think Mercury hasn't been the hot topic that, say, Mars is?
Well, I think hot topic is part of the problem. It's a very difficult planet to study, both when you get there, the amount of thermal radiation, not just coming from the sun, but reflecting off the surface of the planet. Bepi Colombo, which is on its way there, has got some loads of different insulation blankets that have been hand stitched with multiple layers so that they don't stitch between 3 layers or so, because they don't want the thermal conductivity of the thread to go through. It's got a huge amount of cooling and radiation technology, and the radiators have to have fins on so that they reflect away the temperature from the heat coming off the surface as well as radiate out. And not just that, like, it's so close to the sun that as any object moves in, it will accelerate. And so the amount you need to slow down, you need a huge amount of change in velocity to get into orbit around the planet. In fact, I think the amount of delta V, the change in velocity, to get into orbit around Mercury is greater than doing a flyby of Pluto. So it's quite a difficult mission. So every mission that's gone there, even the Mariner 10 that just did flybys, has used gravity assists from Venus to get there. And Bepi Colombo, it's an interesting mission. It's joint European and Japanese space agency, and it's 3 satellites in one. It's got an orbit. The Japanese orbiter is to study the magnetic field and the space environment around Mercury. Then it's got the Bepi, which is the European orbiter, that's going to be orbiting closer to the planet and study more the geology and the chemistry of the planet. The third thing is basically the Mercury Transfer Module, it's called, and it's basically 4 large thrusters and huge solar panels, because they're ion thrusters, and large tanks of xenon gas just to get it there. So they've built a whole satellite portion of it just to help it get there, because it requires so much to slow down. And even then, it's going to have multiple flybys. I think it's 2 Venus flybys. It's already had 1 Earth flyby, and then there'll be 6 flybys of Mercury all the time, trying to shed velocity using the gravity of the planets to slow down until it gets into orbit around Mercury in 2025.
Yeah. Is it going to have quite a sustained orbit, or will it ultimately just crash like Messenger did?
I don't think there are any purely stable orbits around the planet.
Okay.
Crash into it, but it's the MEO, which is the Japanese module, has no thrusters on board. So once it's released, it will eventually end.
Yeah.
Bepi has going to have some fuel on board, so it will be able to adjust it and kind of hopefully try and keep the mission going as long as possible.
Yeah, but ultimately, yeah. So I guess in that respect, then I suppose trying to do a sample return mission then probably isn't really feasible with sort of current levels of technology, I guess. Then
be possible, I think, but not any time soon.
Yeah.
But
I mean,
also,
oh, sorry, David, go on.
Because also, I mean, the surface gravity of Mercury is about the same as Mars, so it's still got, even though it doesn't have an atmosphere to get to, and so you can't use it to slow down, unfortunately, to land on, you still have a decent gravity well to get out of. But next best thing, a lander would be great, because that would still give us a lot of in situ information.
Yeah,
so.
absolutely, yeah, for sure. Yeah.
So as we said at the start, you've just submitted the thesis, and Bepi Colombo all that data sounds like it's going to be amazing. Is that something you're hoping to work on in future?
I would love to. Yes, that would be great. Unfortunately, it doesn't actually get to Mercury until December 2025.
Yeah.
And we're not expecting any science data until 2026. So we'll have to see if closer to the time, if I can get in the mission. It would definitely be great to follow.
Yeah. But stepping back in time then, so what brought you into planetary science in the first place?
So as a kid, I was always a bit of I did enjoy going outdoors, and then I loved dinosaurs and volcanoes. And so I actually studied geology. I was lucky enough to study geology at A level, which isn't offered too much anymore. But then I did geology at university, did a master's project studying gold deposits in Romania, and then went off to work for a mining company in Africa for 5 years.
Oh, cool.
I was working in Liberia doing proper green mapping on the ground, pens and hammer in hand. And then all the time I had a lot of, even because I was in fairly remote campsites, I had a lot of time to look at the night sky. And I have always also enjoyed astronomy. I didn't have the maths to do physics or anything like that, so I never really followed that path. But when I was coming to after about 5 years, I was like, probably need to think of something else to be doing now. And so, yeah, just saw that Dave Rotherham, my supervisor, had this geological mapping of Mercury project, because I was looking around at planetary science. I was like, well, I have a lot of experience with mapping, and I love planets. Let's try and combine these together. And I knew so little about Mercury. I thought this would be quite interesting an interesting body to find out about. So, yeah.
That's brilliant. Do you miss at all the more feet on the ground fieldwork aspect to this kind of work, or?
Yes, I do at times. Being able to because I did a lot of satellite interpretation then, and then being able to go, right, now I've discovered these structures. Let me just go out and check that they're actually there,
Yeah.
and be able to work out if I'm mapping real features, or if I've just seen something that may actually not really be there, which is a problem with some satellite imagery. If you're looking at a forest, you see a feature, all of a sudden it turns out to be a road. But hopefully there aren't too many of those on Mercury.
So how was it going from industry back into academia? Like, I feel that's something not many people talk about. They seem to either disappear into one side or the other.
It's definitely a bit of a culture shock. They're very different, ideas of time pressures and things like that, but also projects on a lot longer phase where you don't have to be the milestones that's much further away with a PhD. I think 3 years, whereas I'd be thinking that's the long-term age of the project, but I've got to hit this in 6 months. And there's lots of different corporate pressures and things like that come in, which is a very different experience to this. But also possibly there's more paperwork involved with writing grants and stuff like that is much more involved in academia. You have to do a lot more individual things that maybe is spread out between multiple people in industry that have skills in those areas.
Yeah, that's a good point, isn't it? Yeah. So would you consider going back to industry then, do you think, or would you like to stay doing planetary science?
There were advantages and disadvantages to both, and I find both quite stimulating. I think as long as I find a job that keeps my brain working and is
Yeah.
involved with some form of remote sensing, whether it's other planets, which would be amazing, or if it was still back on Earth. I mean, Earth is still a planet, and there's still interesting things to find out. It's probably in many ways the most complex planet, so be able to study different aspects of that, even in more of an industry-based area, then that would also be great. I'd be happy with either.
Yeah,
That's a
that's good.
non-answer for you.
Well, I suppose that's the good thing about remote sensing. I mean, there's going to be satellites imaging everything at some point in the future. And also it works quite well for all of us stuck at home to just not be relying on lab equipment or doing field work. So
Yes, definitely. You don't have too much interruption if your satellite you're studying crashed into Mercury in 2015.
Yeah. So like, I know the group, Dave Rothery's group, there's a good team of mappers there. Are there many other groups like in the UK or like in Europe studying Mercury?
Oh, there were definitely. So Leicester, they are looking more composition, because they're looking after MIX, the X-ray spectrometer. So they are studying those more from that point of view, looking at some of the data from Messenger that's applicable. And then there are several different people over Europe looking at the spectral data, or also a few people looking more focused at some of the morphological features, some of the tectonic features. But and so the mapping is spread out, but I don't think there's any institution that is quite as focused on the mapping as we are in the Open University. But even then, all of us who are doing mapping are studying one or two other features, whether it's me looking at some of the volcanic vents. Chris Malaband has been looking at landslide features and downslope movement collapse features. And then Jack Wright was looking at these features that are called knobs, which are cones on Mercury formed by the volatiles vapor moving away and collapsing into these cone shaped. So we all have side projects as well as mapping going on.
We'll edit out John laughing then.
What, knobs?
Yeah.
They are in the literature as Odin's knobs.
Excellent.
Oh, wow.
Yeah. That's named by Americans who I don't think necessarily have the same
Yes,
connotations
that
as
makes
us.
sense.
Yeah.
Well, anyway, moving swiftly on. So, David, I guess we'd better start sort of wrapping up here. But we have one final question that we'd like to ask all our guests that come on, and that is, if you hadn't gone into the world of mapping in planetary science, or in industry, what sort of thing do you think you might have done as a career?
Oh, that's a difficult one. My fallback is always in my mind is tree surgeon.
Okay.
I think that would be a lovely job, outdoors, and get to spend some time looking after trees, stuff like that. Yeah.
Well, that's probably quite an important thing to do.
This might be a dumb question, but what do tree surgeons do? I just picture someone with a chainsaw stood next to a tree. I don't really know what else.
I think that's a lot of it. If there's any damaged part of a tree or ill part of a tree, they'll cut it off. I think they'll do some some preservation if possible. But yeah, they look after trees basically, which mostly is lopping parts of them off.
Pollarding, is that right?
That's a technique for looking after and maintaining trees. Yes.
Yeah, cool.
Yeah, I imagine you'd get to work in some nice national parks or something like that to do it. So that sounds lovely.
Potentially, I think that's more potentially, or also just in suburbia, looking after trees that are blown over in storms. I think it depends where you are, but either way, I think it's an outdoor job that's very different from anything else that I've ever done. That it just sometimes appeals to me.
Yeah. No, fair enough. That's cool.
Well, it's wonderful talking to you, David. Thank you. I can't believe we've not had someone on to talk about Mercury sooner.
Yeah, that's shameful, isn't it, really?
Yeah.
Well, thank you very much for inviting me. It's been great fun.
But yes, no, so David, thanks very much for joining us. And for all you lot in the audience, thank you very much for tuning in once again to another episode of the Cosmic Cast. Don't forget, you can follow us on all the social medias everywhere, the Facebooks and Instagrams and the Twitters and all the rest of it. All the links are in the episode description and on screen right now. But in the meantime, thank you all, and we'll see you again next week. Bye.